Um, Hi, I'm Yanai, and today I'll be talking about complex common sense reasoning and why we're not there yet. So, a bit of history about state-of-the-art NLP. In 2017, a new deep neural network architecture was invented called the transformer. It looks like that. It involves multiple multi-head attention and feed-forward network, and each one of these blocks can be repeated multiple times. Then, in 2018, the architecture was used to train a big language model to predict words in context. So we started with Elmo, which was actually used with a Bar-Ilan architecture, but then BERT came, and since then we're stuck with a bunch of Muppets. So today, to build your state-of-the-art NLP system, there are 3 steps to do. First, pick your favorite Muppet, like BERT. Then, bring your own dataset and train on top of that. Finally, rock your favorite leaderboard. So in NLP, we have a bunch of benchmarks like glue and superglue, which contains multiple classification tasks. And if you go to this website, you can see they are dominated by the Muppets, and they even reach agreement scores and more than that. So is our job done, and can we go home? In this study, I'll show you recent research that we did on common sense reasoning, more in particular on the Winograd schema. This schema was introduced in 2011 as an alternative to the Turing test. And this is a quote from that paper. Moreover, the test is arranged in such a way that having full access to a large corpus of English text might not help much. And this is a very interesting sentence because it's quite ahead of its time. So in today's NLP, the first step with this transformer and language model is to train on a lot of text. And this test was designed especially in such a way that these kind of models won't be able to solve it. They need something more than that. So let's look at a few examples. The trophy doesn't fit into the brown suitcase because it was too large. The task is to say if it refers to the suitcase or to the trophy. So it's basically a co-reference problem. Here's another example. John made sure to thank Susan for all the help she had given. And again, we need to say if she refers to Susan or to John. In this case, it's Susan. So why is this task hard? Actually, for humans, the task is quite easy. We reach high agreement scores and we perform quite well. On the other hand, for machines, the task is quite challenging. First, there's no clear correlation between the entities and the pronouns, right? So she and Susan or John are not necessarily correlated. But also the attribute that is attached to them, like given, is also not correlated, especially with Susan and John. So this task was considered quite hard for multiple years, and until recently, model performance oscillated around random. But now things look differently. This is a screenshot from the Winograd leaderboard, and it seems like we almost reached human performance. So again, the question is, did the Muppets solve it? I'll claim that not quite yet. Here's the first problem. We found that the model performed better than random, even when given only partial information. So here's the same sentence with the trophy and the suitcase from before. We perform a transformation, which we call partial sentence, that takes only half of it because it is too large. And now it's no longer possible to solve the task because what is too large? However, if model can still perform well or above random, it means that there might be some biases and maybe there's still some statistical correlation in the data or in the model. Let's look at the results. On the left, we see the results on WSC. And it seems like the performance gap from random is quite large. So if random is 50%, the model that only gets partial information gets more than 65%. So it's quite a big gap, and it means that maybe the model is using some other correlation and not actually performing the task that was intended to. On the other hand, on the right side, we have the performance on Winograd, and there the gap is much smaller, meaning that this dataset is probably less biased. The second issue, and maybe the more crucial one, is that training on common sense reasoning is future. And what do I mean by that? First of all, the common sense space is huge. And it is evident from the multiple datasets that came in recent years. Each of them is quite large. So if you only have 10,000 or even 100,000 examples, is it really enough to learn all the common sense reasoning in the world? Probably not. Second, the generalization is quite limited. And I'll give you an example. If we had, for example, an example with the strength of the wood in the training set, can we really say or generalize about the strength of steel or styrofoam? Probably not. So instead, we propose to evaluate common sense reasoning task in the zero-shot or few-shot setting. As such, we make use of the mass language model as the way it was trained, to not change the distribution or to show it something that it's not used to. In this case, with the trophy and the suitcase, we just ask it to complete the word, here either large or small. So when we look at the results in the zero-shot setup, first of all, we see that the results drop with all models we tried. And on the left, we see the results on WSC, which is the original dataset. And they're quite low, but still larger than random. But if you recall, we showed earlier that this dataset is quite biased, and it's also small. So maybe it's not the best to look at this dataset as an evidence. On the other hand, on the right, we have the results on the well-grounded dataset, and here, all the models perform much worse than random. So what do we learn from that? Although the leaderboard seem to be solved, we're still far from human agreement. Okay, so what did we achieve in NLP until today, and where are we headed? So the NLP today, its models are getting bigger, and the training corpora also. And we're almost achieving human performance in many of these datasets. And the increasing size allowed them to memorize many parts of the internet. And this may result in good representation, and combining it with large dataset, we often can reach human performance. So this is good in some cases where we're interested in solving a dataset, but it's not really proper generalization and meaning understanding. So it's important to remember that reading the entire internet doesn't make you smart. And although this language model have a lot of capacity, they're just statistical models. And that's what they can do. They collect statistics and correlations about words and the interactions between them, and nothing more than that. They don't really possess any meaning. So in the future, I think we are moving towards better evaluation. For example, more than a single evaluation metric for each task, and additional measurements like the size of the model and the latency. And regarding the models, I think we should get models that actually have common sense knowledge and reasoning, that model that can make causal inferences and are grounded in knowledge. So thank you for listening.